Good afternoon, everyone. My name is David Shehee, and I've been with SWAN Analytical Instruments for about 2 years now. I have a master's degree in analytical chemistry, my Class 4 drinking and distribution operator in Kentucky, a Class 2 wastewater and collection system operator in Kentucky. I have about 18 years managing water quality and environmental compliance of 3 water treatment plants and 4 wastewater treatment plants for a large system in Kentucky with a capacity of about 85 million gallons a day. I've got extensive experience with SWAN instruments. Even prior to joining them, I use their instruments in my plants, so that allows me to attest to their quality, the ease of use, and the cost savings from using their instruments over time. Today, I'm going to be covering off on online turbidity monitoring, and I'm going to be providing you some basic information, but I hope it's useful as you're considering how you move forward with your plant turbidity monitoring. So first, we're going to talk about turbidity. I'm going to talk about what it is, give you a little bit of history of the measurement, and we'll talk about why it's important. I'm going to cover the measurement principle that manufacturers use to monitor turbidity. And then we'll talk about some interferences that create headaches for end users, such as yourself. I'm going to cover off on contact versus non-contact turbidimeters and some of the ongoing maintenance costs like verifications and calibrations. And then I'll give a summary at the end to go over what we've talked about and try to pull it all together in a nice bow. So when we're talking about turbidity, what exactly is it? Well, ASTM, the American Society for Testing of Materials, defines turbidity as a measure of scattered light that results from the interaction between a beam of light and particulate material in a liquid sample. AWWA and the Water Environment Federation describe the cloudiness of water caused by suspended particles such as clays and silts when talking about turbidity, chemical precipitates such as manganese and iron, and organic particles such as plant debris and organisms. Finally, the US EPA describes turbidity as a measure of the cloudiness of water. And honestly, most of utility folks, when we are having customers do tours or offer any type of plant tours, when we're describing turbidity, we typically use the US EPA description, and that's just to measure the cloudiness of water. And that's because when we see this example here from 0.05 up to 800 NTU, as the water gets more cloudy, there's more turbidity. So it's easy just to call it a measure of the cloudiness of water. When we're talking about the history of the turbidity measurement, it's one of the early parameters that was tested. In fact, even before we began testing for it, people were aware that it wasn't a good thing. Think about ancient civilizations, even they decanted water in jugs or used some type of cloth to do that. When we did start measuring it around 1912, the normal procedure used the turbidity standard adopted by the US Geological Survey. And basically what that was a rod with a platinum wire on the end was calibrated by placing graduation marks on the rod at various distances from the end. The rod was lowered into the water as far as the wire could be seen. The vanishing depth was compared to a table of known values to get the measured turbidity. Now, this procedure was used for about 21 years until the Jackson candle method came along in 1933. And the Jackson candle turbidimeter became the standard at that time, and the readout was expressed as Jackson turbidity units. This is actually an example of an old Jackson candle. It helped me describe a little bit more what you're looking at. But basically, a water sample was poured into the top of the tube. The candle was lit here on the bottom until the visual image of the candle flame viewed from the top of the tube is diffused to a uniform glow. When the intensity of the light scattered equals that of the transmitted light, the image disappears. And then the depth of the sample in the tube is red. You can see there's markings on here. When that water sample is at that level, you take that reading and compare it to a ppm silica scale, and that gave you your Jackson turbidity units. This method was actually in use for about 37 years. It wasn't until the 1970s that the Nephelometric turbidity units that we use nowadays was developed. So why is turbidity important? Well, first of all, I don't know about you, but I don't want to go drink water out of a stream that is extremely muddy. It doesn't look good. So from an aesthetics perspective, if I get up in the middle of the night and I get a glass of water out of the tap, I expect that water to be clean and clear. It gives me some confidence that the water is also going to be safe. But turbidity is also an indicator. It indicates the water quality and the effectiveness of the filtration used. It's also regulated. The EPA regulates that treatment plants should optimize to obtain turbidity levels of less than 0.3 NTU in 95% of samples, filtered samples, and that the value should never be greater than 1 NTU. The biggest issue with turbidity is that higher turbidity levels are typically associated with higher levels of disease-causing organisms such as viruses, parasites, for example, Cryptosporidium, which you see in this picture, and some bacteria. High levels of turbidity can protect microorganisms such as viruses, parasites, etc., from the effects of disinfection, and may also indicate Cryptosporidium can break through the filters and enter the water supply. In fact, in 1993, the largest U.S. waterborne disease outbreak occurred in Milwaukee, Wisconsin, causing illness in more than 400,000 people. During the outbreak, one of their water plants had effluent that had a turbidity approaching 2.5 NTU. Now, we all understand that's a pretty high value when we're leaving our plants with 0.02, 0.03 normally. But look at the difference between 0.05 and 20 NTU. You can see why a consumer would not likely be able to distinguish between the difference between 0.05 and 2.5 NTU. They wouldn't know not to consume it at 2.5 NTU. So that's why EPA came out with LT2, the Enhanced Surface Water Treatment Rule, where they allow an additional half a log of Cryptosporidium removal for CFE performance and individual performance less than 0.15 NTU and never greater than 0.3 NTU. You can get a half a log of removal credit for that. Also, it's why voluntary optimization organizations like the Partnership for Safe Water, the Area-Wide Optimization Program, they target a value of 0.1 NTU as opposed to 0.3 NTU. So that's to make sure that we don't have Cryptosporidium or other disease-causing organisms getting into our finished water. Now, as I said, the standard of measurement now is Nephelometry, and that's from the Greek nephele for cloud. It's basically where you send a light of an appropriate wavelength through a sample and detect the intensity at an angle from the incident beam. So here we have a light. So it might be an incandescent bulb, it might be an LED, a laser diode, and we're sending light into a sample, and notice that this sample, there's different particle sizes. Even though if you looked at the sample, you wouldn't be able to notice the different particle sizes in the sample, there are different particle sizes, and that impacts the results. Because of those different particle sizes, research showed that measuring at a 90-degree angle from the light source that's considered to be the least sensitive to variations in particle size. Now remember, we're not measuring attenuation, that is how much light is absorbed by the particles, although that does impact the result. We're measuring the scattering at 90-degree angles from the light source. We use the 90-degree incident angle because, again, it's least sensitive to variations in particle sizes, but it's also what EPA has included for in their methods. EPA 180.1 specifies a white light source at a wavelength of 400 to 600 nanometers at a 90-degree incidence angle. It's also in ISO 7027, where it specifies infrared light at a wavelength of 860 nanometers. Now, in measuring turbidity in drinking water, readings are from a calibration curve established with formazine typically. And the concentration is based on the light scattering properties, and results are typically expressed either in FNU, which is formazine Nephelometric units. That's used internationally through ISO 7027, or NTU, which is the Nephelometric turbidity unit, which is used here in the States, and it's outlined in EPA 180.1. Now, what are some of the problems that we as end users deal with when measuring turbidity? Well, there are different types of interferences that create headaches for us as end users. The measurement of turbidity is subject to a combination of different interferences. Now, all manufacturers like SWAN work to address these interferences as much as possible in their instrument designs to reduce the headaches it creates for the end user. How manufacturers address these issues can make a huge difference in the long-term cost of ownership and also the necessary upkeep, how much time we're having to spend as end users to make sure that instrument is giving us the readings we need it to give us. Now, when we're talking about interferences, we're talking about things that either cause a positive or a negative bias. A negative bias results in a measurement being below the true reading. It's typically associated with measurements greater than 1 NTU, and it can become more significant as the value increases. Now, when we talk about positive biases, that results in a measurement being above the true reading. And it's typically associated with extremely low turbidity measurements, less than about 0.1 NTU. And these are very significant in filtered drinking water and can impact our bottom of filter readings, our combined filter effluent readings, or even our plant effluent readings. So let's cover off on some of these types of interferences. When we talk about absorbing particles, remember, we're measuring scattering at a 90-degree angle, not attenuation. But any particle absorbance would reduce turbidity artificially, as it wouldn't reflect. It would be absorbed by the particle. So you could see where that could cause a negative bias. Also, color in the matrix. It can cause a negative bias if the incident light overlaps the absorptive spectra within the sample matrix. Now, particle size can cause either a positive or negative bias. It's wavelength dependent. Larger particles, remember we talked about that samples have smaller and larger particles. Larger particles scatter long wavelengths of light more readily than will small particles do. Small particles scatter short wavelengths of light more efficiently than long wavelengths. Now again, that's accounted for by the use of the 90-degree angle by all manufacturers. When we talk about bubbles, or air trapped in water, that can cause a positive bias. Now, there's lots of different ways to address this, but it must be accounted for by all manufacturers. Why is that? Well, one, colder water holds more dissolved oxygen than warmer water. So what happens many times in colder climates, the water has a lot of dissolved oxygen in it. It comes into the plant, and where the water is where the temperature is warmer, that water warms up. It can't hold all that dissolved oxygen, so it releases that dissolved oxygen. Those of you in colder climates know that sometimes your customers may call you and tell you they've got milky water, and that's typically just thousands of air bubbles that you can't see that they're bubbles, but it is indeed bubbles. So that can impact the reading. Also, if you're pumping water to your filter, if you're pumping it to your combined filter effluent, your raw water, that can introduce a lot of turbulence and air bubbles as a result. So those have to be addressed by manufacturers in some capacity. And then let's talk about sample cell variations. Now, these can cause either positive or negative bias. Now, remember, many of us have used benchtop instruments for years. So you had to apply silicone oils to reduce reflections due to scratches, and you have to polish the cuvette to make sure that the sample cell is clean and it's not affecting the reading. Now, this is also starting to become an issue for some of the newer online analyzers because they use cuvettes, and we'll discuss that a little bit more in the slides to come. When we talk about stray light, now, many times we don't worry about stray light, but manufacturers should be addressing this, and I'll talk a little bit about how SWAN does that. I can tell you that I once had a combined filter effluent turbidimeter that was reading about 0.07 NTUs when my individual filters were all 0.02. Now these were prior to me going with SWAN. I worked with the manufacturer of that instrument to determine that the bottom of the unit was fading over time, and it was allowing stray light from light reflection to negatively impact the result. It was creating a higher number than was actually there. So that's something that needs to be addressed in some capacity to make sure that you're not getting higher numbers than you should. Now, there are also instrument-based effects too. So for example, what light source are you using? Is your light source going to degrade all the time? You know, is there going to be fouling due to iron and manganese and excessive humidity? Is there electronic drift issues, noise from the electronics that could cause a bias in the results? And as I said, all manufacturers try to address these issues, but again, how it's accomplished impacts the cost of ownership to you and the amount of headaches that you encounter to maintain the instrument. So let's talk about contact versus non-contact. When we're talking about contact turbidimeters, there's lots of different designs on the market. Some of the older instruments had a reservoir with a submerged sensor. Some of the newer ones have a flow-through design or cuvette design. But the commonality in all of these is that a contact turbidimeter has one component of the instrument at least that will have a direct impact on the sample result. For example, the light source, the lens, the cuvette, or the detector that is in direct contact with the matrix. And that can create a lot of issues and maintenance issues that you have to deal with in the long run. Now, when we're talking about a non-contact turbidimeter, let's talk about the SWAN instrument. And the non-contact means that you can avoid fouling of the instrument due to things like iron and manganese. Because again, when the detector or a cuvette is in direct contact with the sample, you're going to have to clean it periodically. You're going to have to replace a cuvette periodically. You're going to have to address the iron and manganese staining. How often that's required and how it's performed can be a huge issue for plant personnel. Or if you're having somebody come in and do it for you, it's going to increase your cost significantly. Again, this isn't an issue for a SWAN turbidimeter. Now, a SWAN turbidimeter, this is a side angle of it. I'm going to show you some other views. It has a constant head chamber to keep the sample level in the sample chamber where it should be. But what's nice about that constant head chamber is it also removes most air bubbles. So unless you have a tremendous amount of air bubbles in the sample, this constant head chamber is going to remove the majority of them because the sample inlet comes in here, it comes up, and the majority of the sample goes to drain, but it allows enough to come into the bottom of the instrument and flow up to where it's going to get seen by the photometer and the LED light source. Now, an optional degasser is necessary. If you just have a tremendous amount of air bubbles, you can get this optional degasser here, and it is fantastic. I had it on my units at my plant just as a precaution, and I can tell you it removes all air. It will be of no issue. I had several that had pumps that got the water to the turbidimeter, and air never played an issue in our readings. So Some other things that are really nice about this turbidimeter, it has a specially designed chamber, both in the way that it slopes and allows everything to funnel to the drain at the bottom, so you don't have additional sediment collecting in the bottom that doesn't get flushed out, so you have to try to reach your hand in there and clean things out. But it also has a beam trap in here. Remember, we talked about stray light. That beam trap traps any stray light that could increase the number. It also has an auto zero feature every night that also eliminates any stray light that may impact the result. And basically what that is, it shuts off the LED light source and it allows the detector to read if there is any stray light coming in, and it will subtract that out of the value. The unit has electronic drift stabilization to eliminate any impact due to stray current. The optics are heated to a constant 40 degrees Celsius to address any condensation that might occur, especially if it's in a pipe gallery during the summer months when you've got a lot of sweating on pipes. Because the optics are heated, you as an end user are not required to periodically change a desiccant or to clean the instrument to ensure a moisture-free optical path. As I said, this instrument uses a white LED source. It emits a wavelength at 400 to 600 nanometers due to the EPA regulations. It's a high quality, long lasting LED light source that has a sensor that is looking at it all the time to monitor the intensity, and it will auto correct it if it starts to fade over time. SWAN has had these instruments in the field for over 10 years now, and we have never had a bulb failure. That's how the quality of these LED bulbs that we use. One of the things that I really like about the instrument too is the instrument goes into auto hold mode when the top is raised, and it'll automatically go back into operation when the unit is closed. The amount of time it's in the hold mode can be programmed. And this reduces the potential for a violation for not taking your 15-minute readings. I once had a manufacturer come in, they were doing my quarterly calibrations. They put the unit in a manual hold. They forgot to put it back in the run mode when they left. The unit was sending the held signal, so the operators didn't notice it for a few days, and we ended up getting a violation because of it. What's also nice is because the way this instrument is designed, the head is attached to the body. So it isn't necessary to try to find somewhere to place parts or to hold the head when you're performing maintenance, which I really like about the unit. It also has an automatic flush device that you can get as an option. That's really nice if you have a raw water source, especially if you have the turb like at the intake and maybe the intake is a couple miles away. You don't want to have to go out there and flush it periodically. This will automatically flush it for you and make sure that the instrument stays clean. And finally, it comes with an industry best 4-year in-plant warranty to cover any manufacturer-related instrument failures. So you're not going to have to worry about something going wrong with this instrument and you're having to come out of your pocket with more money to fix it for 4 years. So here's a little bit how this instrument works. As I said, water flows in through the bottom. You got your LED light source and your detector. They never contact with the water. The LED light source shoots a light. The detector measures it at a 90-degree angle per EPA 180.1. There's the beam trap that catches any stray light. All your sediment settles out to the bottom and away from the light path. And then, of course, the bottom mounted drain removes buildup. When you open that drain, it automatically flushes out, which is really nice. So when we talk about verifying, a verification is different than a calibration. Remember, a verification is just verifying that something is performing like it should. So verifications can be performed by comparing it to a benchtop. Some states allow this comparison and give a 0.05 NTU window for samples less than 0.5 NTU. You can also get a verification kit from SWAN, and that can come as a primary or secondary standard for verification purposes. You can actually use the primary kit as a calibration mechanism too, and we'll talk a bit more about that. It's very accurate and it's very simple. It's placed in the flow cell and it's mounted flush for integrity of the measurement. And there is a little pin on the unit. I'll show you that in a little bit. And it just sits right in this hole right here. And it just mounts in there flushly and sits in there perfectly. So there isn't a lot of movement that you have to worry about to try to get it in the right place to read properly. When you first get the unit, you will match the verification kit to the unit, which is a really nice feature, and it allows your verifications to be much smoother. It's a menu-driven process that walks the user through every step of the process, so there's not a way to make a mistake. It has factory programmed acceptance criteria, and all information like the verification value, the time, and the date, it's all saved in the diagnostic menu. It'll hold up to 32 readings, so you get about 8 years worth of verifications that's stored in the monitor for you. It's a very quick procedure. It only takes about 2 minutes to complete, which is another thing that's really nice, especially if you have a large filter gallery and you have to do 20 or 30 of these things. When you perform the procedure, you drain the instrument body, and that cleans out the turbidity in the unit. Because iron and manganese staining is not an issue, additional purchases aren't necessary to make sure the instrument remains clean and performs properly. And again, we only recommend that you do quarterly verifications, and so this can reduce costs significantly. I know with our previous manufacturer, we did weekly verifications, so my folks really loved going to this instrument and doing quarterly verifications, and we found that these units don't drift, so quarterly verifications were perfectly acceptable. I'm going to show you a quick video here of how matching and verification is done.
The following solid verification kits are available. The matching procedure is menu guided. In case a new VeriKit is to be matched, proceed as follows. Define a unique name for the VeriKit. There are 10 characters available. The assigned value is shown on the label of the VeriKit. All matched VeriKits show up on the list and can be selected to repeat the matching. Proceed as shown on the display. Carefully take the VeriKit out of the box. Avoid touching the optical surfaces when working with the verification kit. Insert the VeriKit and ensure that it is fastened correctly. Close the measuring chamber and start the matching by pressing Enter. The values of the matching are saved. In case the matching was not successful, the following error message will appear. The verification procedure is menu guided. Choose the desired VeriKit from the list and proceed according to instructions on the screen. To avoid misting of the glass prisms, make sure that the VeriKit and the measuring chamber have the same temperature. Insert the VeriKit and ensure that it is fastened correctly. Close the measuring chamber and start the verification by pressing Enter. The values of a successful verification are stored. In case the verification was not successful, the following error message will appear.
All right, so that shows you how matching and verification is done. And SWAN, as I said, offers a couple of different verification kits. We have a primary standard verification kit that comes in a box like this, and it has 4 vials with 4 lids, obviously. And it's recommended, as I said, that you do this quarterly, whether you're using a primary or a secondary. And because this is a primary and you're going to be using a primary standard, and we recommend 20 NTU, that's what works with this particular kit, you can use it for calibration, which is really nice. Now, this primary standard verification kit has a mounting pin, and it holds about 2 to 3 mils of 20 NTU standard. You can use that same standard to do all your instruments. So you probably run out of date on the standard before you will use it all. So even if you had 30 instruments, you can use that same little vial to do all of them. You want to fill this up to 0 headspace like a THM or HAA sample. And when you're done with it, you want to rinse it out after each use to remove all the residues with, use DI water. And this just pushes into the unit just like this. You can see it flush on here. Here's another picture of it with the lid on and placing it in the instrument. Sits in there just the same way. So it's a really nice, handy tool to do a primary verification. You can also get a secondary verification. Verification kit, sorry. It looks very similar to the primary, except it uses acrylic glass prisms here. It also has a glass down on the bottom that I'll show you that's different from the vial that's stuck in there. We recommend that you recertify this one about every 2 years. You can get longer out of it. You can see when it starts drifting on you, but usually we recommend 2 years. As I said, this is a little bit different from the primary in that you slide the vial in the primary here, but this one has turbid glass that uses scattering of the light beam like water. The plexiglass prisms simulate refraction of the water. Those same prisms are there on the primary standard as well. This is the only difference between the primary and the secondary. Now, when we talk about calibration, let's talk about why it's needed. You should only need to calibrate an instrument when there is electronic drift, when there is light source degradation, when there's stray light that's causing a problem with the reading. The most significant drift results from minute contaminants fouling the optical elements, for example, iron and manganese. Now, the slope of the calibration is predefined and stored in every instrument. SWAN's factory calibration includes a 0 point, as we believe it's essential for the low-level measurements being performed. Some manufacturers don't take this approach. The reading indicated by turbidimeters, again, are not scaled in light intensity, but in the concentration of a reference suspension. Since the accuracy of the calibration solution determines the accuracy of the turbidity measurements, it's of crucial importance. That's why SWAN's recommendation is that the instrument should not be calibrated in the field for optimal performance. Now, you can also do a calibration of the SWAN turbidimeter if necessary, just by placing a rubber stopper in the drain, the overflow drain, and filling the body with a 20 NTU formazine standard. It works very similar to the primary verification kit. Honestly, I've done both. The primary verification kit's a little bit simpler, and obviously you'll use a significantly less amount of formazine standard. The SWAN turbidimeter is approved from EPA using an alternative method to 180.1. You can find that method at www.nemi.gov. That's the National Environmental Methods Index. And this method calls out the fact that SWAN uses an LED bulb instead of a tungsten light source, and also that we recommend verification rather than calibration in the field. So let's summarize quickly what we've talked about in today's presentation. We talked about entrained air or air bubbles. This is a problem for every manufacturer. SWAN, again, has the constant head chamber on the back of the instrument, so that typically addresses all air bubbles. However, you can get an optional degasser for the unit if you have a tremendous amount of air bubbles. And so most of the time you won't need it, so that's going to save you dollars. We talked about stray light and how that leads to errant readings and dollars to fix that problem. Again, our instrument has a beam trap and it takes a dark 0 every night, so you're not dealing with any type of stray lights. In terms of light degradation, remember that SWAN has an LED bulb, and also it has an auto correction where it's looking at the intensity of the light and it will auto correct for that, and that ensures long-term accuracy of the instrument. In terms of optic fouling, you're not going to have that because, again, there's no staining or from iron and manganese that's going to be a problem because it's a non-contact turbidimeter. There's no impact from electronics because SWAN uses electronic drift stabilization. There is no replacing of desiccant or cleaning of cuvettes due to condensation issues because SWAN uses heated optics. In terms of instrument failure, first of all, you're likely not going to see it with SWAN because all of our instruments and all critical components are manufactured in Switzerland. There are no cheap parts that are on these instruments. They're very particular about how they manufacture all these. That's why they come with the 4-year implant warranty. So instrument failures are not an issue. If you have an issue for 4 years, it's an implant warranty. They're going to come out and fix or replace it at no cost to you. The manual hold NOV, no violations and public notifications because you forgot to take the instrument out of hold when you finished working on it. Again, the verification kit, it's mounted flush in the body and doesn't take special manipulation to work properly. Therefore, the time it takes to perform a verification is reduced. And also, verifications are only recommended by SWAN quarterly, thereby reducing operational costs significantly over time. Again, calibrations are not recommended by SWAN, thereby significantly reducing chemical and/or labor expenses over time, especially if you are having somebody from the outside come in and do those calibrations for you. If you'd like more information about the SWAN AMI Turbo Well Analyzer, or to request a quote, or discuss a trial at your plant of a turbo well, please call us at 847-229-1290 or send an email to our info account at swananalyticalusa.com, or you can contact your local SWAN sales representative. Thank you so much for attending today's webinar.